In this lesson, we will be evaluating nth roots of real numbers using both radical notation and rational exponent notation. So if we take a look first at simplifying some roots, what we want to notice is what type of roots we're talking about. For example, in this we have the square root of 4, and we know it's the square root because it doesn't have a small number in the index, isn't right here. So the square root of 4, this is a square root. We want to know what number times itself gives us 4, and the square root of 4 is 2. Notice there is not a sign out front of the radical, so we are talking only about the principal root, which means the positive square root. When we took a look at the next one, since we have an index of a 3, we know that this is a cube root, and a cube root means what number times itself 3 times is going to give us 125. Now we can find that in a couple of ways. If we ask you to not use your calculator, we can find that by simply making the prime factorization. So 5 times 25, and then breaking that 25 down again into 5 times 5. And so we notice that we multiply 5 times itself 3 times, and therefore the cube root of 125 is 5. Next, we have the fourth root of 81. Again, a couple of ways you could find that, and if we had asked you to do that without a calculator, which would be one way, then we would find or use the prime factorization. For 81, we have 9 times 9, 3 times 3, 3 times 3, and we see that there is the number 3 times itself 4 times gives us 81. And then the fifth root of 32, and we can tell that because we have our index of a 5. The fifth root is asking us what number can we multiply times itself 5 times to give us 32. So we can break that down into 8 times 4, into 4 times 2, into 2 times 2, and into 2 times 2, and we can see that we would multiply 2 times itself 5 times, and that would give us 32. Obviously, the other way to find those different roots would be to use a calculator. So what we need to remember also is that when we find the nth root of a number or variable, we can also rewrite this as using a rational exponent, which means a fractional exponent. For example, if I want the square root of a, that can be written as a to the 1/2 power. If I want the cube root of a, I can write that as a to the 1/3 power. The denominator of the fractional exponent is our root. Here's how I remember that. The root of a tree or the root of a plant is down below or on the bottom. Therefore, that is the denominator of the fraction. The numerator of that rational exponent is actually the power. So for example, if I had the fourth root of a to the 3rd power, we could write that as a fractional exponent. A is still the base, the 3 is the numerator, and the 4 is the denominator of the fraction. The root is the denominator, the exponent itself becomes the numerator. So let's move on to some other examples. This says we are to rewrite the expression using rational notation. So if I have the square root of 7, when we rewrite that with a rational exponent, we will write the base of 7. The base of 7 has an exponent of 1, and then the root is 2. So this is going to be 7 to the 1/2 power. In this example, number 2, again, the base is 2, the exponent is a 2, and the radical is to the root of 3. So that becomes our denominator. In number 3, the base is 12. The 12 is to an exponent of 1, and the denominator is the root, which is the 4th root. So that's going to be 12 to the 1/4 power. Let's try some more. So we have 5 to the root of 3, so that's going to be 5 to the 1/3 power. In the next example, we have a 6th root of 15 to the 5th power. We keep the base, which is 15. The exponent is 5, which becomes the numerator, and the denominator is our root, which is 6. So that's going to be 15 to the 5/6 power. In the next example, our base is 10. 10 has an exponent of 1 with a root of 8, so that's going to be 10 to the 1/8 power. Let's try a couple more examples. In this one, we have our base of 11. 11 has an exponent of 1 with a root of 5, so that's going to be 11 to the 1/5 power. In the next example, our base is 3. 6 is our exponent, and 9 is our root, which becomes our denominator. We also can treat rational exponents as fractions in the fact that they can be reduced. So 6/9 can be reduced by dividing both by 3, and that becomes to the 2/3 power. In our last example, where we are rewriting our roots as rational exponents, we keep our base of 19. Our exponent is a 4, and our root is 7. So this will be 19 to the 4/7 power. Now what we would like to do is we would like to rewrite our rational exponents as radicals. We want to use radical notation. So the denominator tells us the type of root, so we are going to do the square root of 3, and the exponent tells us the power. Since it's to the first power, we don't need to write that. In our next example, we see that the root is a root of 3, which is the denominator, and we have our base of 5, which is to the second power. We can also write this as a root of 3 with 5 being our base, and then we can take this to the second power. These mean the same thing, but would be calculated differently. In the example first one for number 11, we would actually square the 5 to get 25, then take the third root. In this example, we would take the third root first, and then we would square. And we will find out that sometimes that's our better option. In example for number 12, we have 6 to the 1/4 power. Remember, the denominator of the fraction tells us the root, so this is going to be the fourth root. The base is 6, and it's to the first power, which we don't need to write. Let's take a look at another set of examples. So we have 4 to the 1/3 power. So the root is the denominator of the fraction. This is going to be the third root of 4, which is our base, and that's going to be to the first power, which we don't need to write. In the next example, 16 is our base, 8 is our root, so this is the 8th root of 16, and that is to the first power, so we don't need to write that. In this example, again, our base is 25. The root is the denominator, so that's going to be a root of 12, and our exponent is 7. So when we write that, we can either write to the 7th power like this, or we can put the root of 12 with 25 as our base, and then we can take the entire thing to the 7th power. Let's take a look at a couple more. So we have 14 to the 5/6 power. The 6 is our root. We have a root of 6. 14 is our base, and that's going to be to the 5th power. And again, that could also be written as taking the 6th root of 14, and then we would take that to the 5th power. We have 8 to the 1/4 power. The 4 is our root, and then we have 8 as our base to the first power, and we don't need to write that. Our last example on this page, we have 7 to the 3/5 power. So our denominator is our root, so that's going to be to the 5th power, or 5th root of 7 to the 3rd power. We can also write that as the 5th root of 7, and then we can take that to the 5th power. So let's take a look at a couple of more examples. These we are supposed to evaluate without a calculator. So we want the 4th root of 625. So in order to evaluate without a calculator, we simply want to do the prime factorization. So 625 I know is 25 times 25, and I break that down again into 5 times 5 and 5 times 5. So we see that we have 5 being multiplied times itself 4 times, so therefore the fourth root of 625 is 5. Now when we go to the next example, because the negative sign is under the radical, and because we are talking about real numbers in these situations, there isn't a number that I can multiply times itself 4 times that will give us a negative number. So in this case, this will be no solution in the real number system. In the next example, I want the fourth root of 81. Without a calculator, I want to find the prime factorization. So we have 9 times 9 and 3 times 3, which tells us that 3 is multiplied times itself 4 times to get 81. So the fourth root of 81 is 3. In our next example, you're going to notice that we have negative 81 to the 1/4 power. Notice that the negative 81 is not in parentheses. So what this really means is negative 1 times 81 to the 1/4 power. So when we calculate this, we want to find negative 1 times the fourth root of 81. We already calculated the fourth root of 81 in the previous example, which is 3. So then we're going to multiply that by negative 1. So our answer for this one is negative 3. However, when you take a look at an example going down to the second line, we do have our negative 27 in parentheses. So that means I want the third root of negative 27, and then I'm going to take that to the second power. Now in the previous slide we said you could also square the 27 and then take the third root. Either will give you the correct answer, but when you are doing these without a calculator, my best advice is to do the root first because that will give you a smaller number, and then to do the exponent. So when we want to do the third root of negative 27, what we find out is that this is going to be negative 9 and then negative 3, which breaks down into negative 3 and negative 3. Or it's positive 9 times negative 3 and then negative 3 times negative 3. Because we have a negative number, we're going to multiply 3 negatives together. That will give us our negative value. So the cube root of negative 27 is negative 3, and then when we square that, that gives us a value of positive 9. Now the difference being for this example is that since the negative sign isn't with the 27 in parentheses, this really means negative 1 times 27 to the 2/3 power. So that means we have negative 1 times the cube root of 27, and then we're going to square that. Now basically we did a factor tree for 27. Ignoring the negative signs, we know that it's 3 times itself 3 times. So we have negative 1 times 3 squared. 3 squared is 9, and negative 1 times 9 would be negative 9. And that's the difference between using parentheses and not using parentheses. That will give us a different answer. Okay, when we go on to the next example, if you recall with your rules of exponents that if you have a negative exponent, it means we are going to take the reciprocal of the base. And when we take the reciprocal of the base, that makes our exponent positive. So this is going to be 1/9 to the 3/2 power. So what we're going to do is calculate 1 over the square root of 9, and then we are going to cube that answer. So the square root of 9 is 3, so we have 1 over 3 to the 3rd power, and that gives us 1 over 27. In the last example, which is a little bit more complicated, what we need to figure out is that if I have negative 32 to the negative 3/5 power, this means I have negative 1 times 32 to the negative 3/5 power. Remember that we need to take the reciprocal of the 32 in order to make our exponent positive. So this is going to be 1 over 32 to the 3/5 power. So when we simplify, we have negative 1, and then this is going to be times 1 over the 5th root of 32, And then after we do the 5th root of 32, we're going to cube our answer. So talking through that on a previous slide, we took the 5th root of 32. We found out that that was 2 times itself 5 times. So the 5th root of 32 is 2. And 2 to the 3rd power, 2 times 2 is 4, times 2 is 8. So we have negative 1 times 1/8, which is going to give us a final answer of negative 1/8. In our last set of examples, we are going to solve equations with different roots. Remember to isolate the power, take the appropriate root on both sides, and then finish solving the equation by doing opposite operations if necessary. In the first example, we have the cube root of x cubed is equal to 125. So in order to solve, we have the x cubed by itself already. We want to do the opposite operation, which is actually to take the cube root of both sides. So when we do the cube root, we need to make sure we put that right here. If we were to make a factor tree, we would find out that this is 5 times 25, and 25 will break down into 5 times 5. So we find out that 5 cubed is 125, so the cube root will be 5. In the next example, we want to get the exponent power by itself, so we're going to divide both sides by 3. So we have x to the 5th power is equal to negative 1. Now since we have an odd exponent and our value is negative, we would know that any number times itself 5 times to give us a negative answer would need to be negative to begin with. So do the opposite operation, which is to take the 5th root. What number times itself 5 times gives us negative 1? And that's going to be negative 1. In the next example, we want to add 3 to both sides. So then we have 2 times the quantity x plus 4 to the 3rd power is equal to negative 16. And then we're going to divide both sides by 2. So we have x plus 4 to the 3rd power is equal to negative 8. We need to do the opposite operation since we've isolated the power, which means we're going to take the cube root of both sides. What number times itself 3 times gives us negative 8? And that's going to be a negative 2. So we have x plus 4 is equal to negative 2. And when we subtract 4 from both sides, x is equal to a negative 6. In the last example, we're going to add 7 to both sides. And when we have 7, we have x to the 4th power is equal to 10,000. In order to solve, we now have the power isolated, so we are going to take the 4th root of both sides. So we have x is equal to, we want to know what number times itself. 4 times is going to give us 10,000. That's going to be 10. But in this case, we could take 10 times 10 times 10 times 10, all positives, and we'll get a positive answer. Or if all the 10s were negative, remember an even power, if all of them are negative, will still give us a positive answer. So therefore, when we take the 4th root of a number, we know that we need both answers or both solutions, plus or minus 10. To review, please make sure you remember that the nth root of a is equal to a to the 1 over n power. Remember to solve exponential equations by isolating the power, take the appropriate root of both sides, and continue with opposite operations if necessary.